Morning, everyone. Thank you for joining us in RC design class on Monday again. Really appreciate your participation. And while we're waiting for one more minute to get the course started, a quick announcement. I finished the grading almost, except the homework number 6. I'm still a few shy from it, but I should be done by this noon time this morning. And again, the exam grades are all out, and a few quizzes, number 7, number 8, still need to be graded, but that'll be quick. I put a new assignment as assignment number 6, sorry, number 7 homework, that is. Sorry for updating it a little bit late, but if you notice that the deadline is no longer it's no longer this Thursday, but next Monday instead. A few days extension because of the late uploads. And the final announcement is about a quiz. The quiz 9 has been uploaded. And in response of the several students still asking where to find the quizzes, and that shouldn't be a problem, but I still screenshot the problem and upload to the quiz number 9. Okay. All right. So that's where we at in terms of assignment. And going forward, quickly update on the progress of the lecture so far. We have covered mainly the content we'd like to cover. We're on schedule. Now we have the developments and the column design and part of the deflection which we'll finish today, and that will finish the rest of the lectures. And again, we're approaching the end of the semester, so we would like to also put in one lab project. It's basically a course project, but utilizing the content as a lab. For that, we'll do it next week. And I will be traveling next week, and we use that time basically Thursday time next week for the course design. But since I'm traveling, I'll be recording the lectures on Monday and Wednesday next week and upload on the time, during the lecture time. And you can find that through my YouTube channel. Okay. So that's all the information we have. Any questions about this course progress? Any question about homework grades and everything? Anything for me? Folks, are we okay? All right. Yeah. Anything?
Oh, I was going to say, I think we're all good.
Okay, all right, sounds good. And sorry, I forgot to mention one last thing is about the CET evaluation. And most time I don't get a whole lot of responses from the courses, and so are my colleagues in the department. To bump up or to increase the participation rates, and I'll say this again, till we get the evaluation done. That is, if all of us pay attention, if all of us participate the survey and the response rate is higher than 60%. Okay, if I say this again, if all of us participate in the evaluation, online evaluation, and if the response rate is higher than 60%, at the end of the grading, that is after you finish the finals, I will give 3 extra points collectively to all of us. Okay, and this is 3 solid points on the exam grade. That is, after we did all the weighted percentages, you got a grade. And if 60% of students answer the response rate, we all got 3 points out of it. Okay, so I hope this is a incentive for you to finish the evaluation, and please spread the information around. And I'll say this again on Wednesday and Thursday as well. All right. Okay. So that's that, and let's continue with our courses. All right. So lecture 21, service deflections. I'm sharing my screen now, so you should see the title right now. Okay. Now, last lecture we have talked about how to calculate deflections, and that seems to be a little bit complicated. So I decided to make a tiny table, hopefully to structure it even better, right? Hopefully to structure it even better. So let's take a look at the very basic problem, right? So if I have a beam, right? Say I have a fixed support and have a beam like this. Okay, now with this fixed support, let me name the left end is 1 and right hand side is 2 and the middle is middle, right? So the name of the game is to find out the effective moment of inertia, which is IE. Okay, to find out the moment of inertia, which is IE. And if you remember, this equal to a 0.5 I middle, okay, plus a 0.25 of I1 plus I2. Okay, 0.25 of I1 and I2. So that's the upper level. So you can call it level 1. So this is more like a structure level. Okay, so that is the structure level. Now for this mid and IE1, IE2, we have to look at the section level. Okay, section level. So now considering the moment diagram for this, okay, that is assuming the moment diagram for this, it looks like something like this, okay, and let's call it MA. And to be more specific, let's call it MA mid, and this is MA2, okay, and this is MA1. And when I do the cut, right, when I do the cut, you notice that when I get the values, this is just specifically these three values, okay, MA mid, MA1, MA2. All right. Now, when I said this is at the section level, what I mean by that is now the IE mid equal to MCR divided by MA mid to the power of 3 multiplied by IGT, okay, and plus bracket inside 1 minus MCR. This is wrong. This is correct. MA mid, and this is cube, and outside should be ICR. Let me make sure this is correct. Okay, so let me jump out here and go back here. Make sure my correction is correct. Okay, that is right. All right, so with that, we have to put usually, okay, usually, and this is for continuous conditions, okay? This is usually for continuous conditions. That means continuously support conditions. So for the middle span, it usually is positive, okay? So this is positive IGT and ICR. All right. So if you recall for T-beam, we talked about last week, right? For T-beam, section looks like this, and the reinforcements here, and this is the positive bending moment of inertia, right? So everything is looking at a positive. Now for IE1 or IE2, everything stayed the same. So this is MCR. Now, if you really want to take a look, this is positive, positive. Okay, MCR. Now here should be negative. Okay, so let me put this one up here so it'll be differentiate from the lowercase. Now this here should be the moment at the corresponding support. Should be the moment at the corresponding supports. So this is power of 3, and this is IGT, and here is negative. Use the same color, okay? Apologize. Same color, negative, all right? And then coming back, plus the bracket 1 minus MCR again should be MA1 or 2, but here now is negative, and this is the power of a cube. And now multiply by ICR, and now let's use the corresponding negative sign in front of it. All right, okay. So that is how we divide the level, right, or the scale of moment inertias. So IE effective is, you can say it, this is the effective effective moment of inertia for the whole beam, okay, for the whole beam. And this IE1, IE2, IE mid, IE mid, IE1, IE2 are the effective moment of inertia for sections, okay, sections of the beam, okay, of the beam. So they are different, they're different levels, okay. So naturally you need go from section to structure to find your final effective moment inertia for the beam. All right. So I hope this is helpful so you can visualize how we did all this following the last lecture. And you can use it to structure. And in the quiz 9, right? Quiz 9, and be careful in quiz 9. So if I really want to draw the section, since this is negative, so you can visualize in terms if I flip the section and I can get my negative bending moment, sorry, negative cracking and all the other information. All right. And this is in the quiz 9. You have to follow the details we talked about before in finding the cracking moment and moment inertia and such, and do the quiz 9. You have a better understanding of it. Okay. All right. So that is the gist of it. So you have to follow this to get your effective moment of inertia for the beam. Now the question is, how do we utilize, or why do we need the IE? Okay, why do we need IE? Because we want to calculate deflections. So how do I calculate deflections? For example, if I have, if I have a simply supported beam, right? If I have a simply supported beam, okay? And well, actually, I've been using continuous, so sorry about that. Let me just turn it back to a constraint and a fixed support, okay, continuous support, and say I have a concentrated force and I have moment, right? And if I want to find out the deflection delta at the middle span, that is usually we talk about this at the middle span, okay? Deflection at the middle span delta, and that equation usually is 5 over, in this instead, this should be 1 over 384 E I E, okay? And this is L to the power of cube, okay, to the power of cube. So this is where we need the effective moment inertia of the beam, okay? Effective moment of inertia for the beam to find out the deflection, All right, so that was the purpose. We find out the effective moment inertia, we went in and we calculated deflection for the beam, we were happy about it. However, this is not the full story. Okay? Why this is not the full story? Think about it, right? Think about it. When I, for example, start building the structures, right? I do not apply the loading instantaneously, right? I do not put the loading instantaneously. Matter of fact, the loading was applied to the structures by steps or with different time points, okay? So if I to look at this, right, I will look at the picture like this. So initially, I have a beam, and then instantaneously, I put a dead load on it. Okay? So this is a dead load, okay? And this is dead load. And this dead load will give me an instantaneous deflection. That means if I put a load, I will see a deflection immediately. And I call it delta ID, representing instantaneous deflection. Okay, instantaneous deflection. Okay, but as time goes by, right, there are creep in the concrete, and there are boundary condition changes of the beam because things wears out, materials wears out, right? The supports changes, the rubber padding underneath the support, my age. So all these things change the conditions. So to reflect that, we introduced a new term called the time-dependent coefficient. And this coefficient is called lambda. Okay, and that lambda is a function of t. And be careful to differentiate this lambda from the normal weight, lightweight concrete coefficient lambda, okay? This is so-called time-dependent coefficient lambda. So as time goes by, my instantaneous deflection increases, right? By multiplying time-dependent coefficient, And we'll talk about this lambda t, okay? So right now, you just need to know lambda t is a time-dependent coefficient, okay? Time-dependent coefficient. All right, so that is dead load. That is the dead load, right? So when dead load occur, when dead load start to become effective, that is upon construction, right? Upon construction, right? When all the self weight, all the materials weight goes into the structure, boom, you have the instantaneous deflection. Okay. So now after that, right, we say, look, right, we want to add the live load as well. We want to add the live load as well, right? So when I want to add live load, right? So I have to consider one thing. I have to consider one thing. There are two types of live load. Two types of live load, right? So one type live load is the sustained part. Okay, so I call it sustained live load. Okay, so this sustained live load, all right, will cause a sustained, okay? This sustained live load will give me a time-dependent deflection, which means I also have to find a time-dependent coefficient to multiply in front of it to get my time-dependent deflection for the sustained part. But instantaneously, once my live load has put onto it, so this is the remaining part of the live load, okay? I will also have instantaneous deflection, means right away, deflection right away, immediately deflection right away. Okay, so all this constitute the total deflection. Okay, this tiny table here constitute the total deflection right here, components of total deflection. All right, so let's take a look, right? What are the time-dependent deflections now? What are the time-dependent deflections now, right? So essentially what we're saying is delta deflection total, okay, should equal to several part, right? Several part. Now, since the instantaneous dead load induced deflection will be there from the get-go, right? So we say that the first component will be lambda, a time coefficient, right? Time coefficient. This time coefficient should be starting from t0 to infinity. What does this mean, right? T0 is the time when dead load is applied. Time when dead load was applied. Okay, infinity is as long as the structure stands, as long as the structure stands. So this coefficient multiplies delta I d, all right, plus a an instantaneous deflection caused by the live load delta IL plus a lambda infinity, lambda 0 to infinity multiplied by the delta LL, which is delta live load. Okay, so let me put this off here. Okay, and this is the sustained part of live load. Sustained part of live load. Deflection caused by the sustained part of live load. All right, so that is the composition of total deflection. Let me say this again, okay? The composition of total deflection comes from three sources. The first source is the time-dependent coefficient multiplied by the instantaneous deflection, okay, caused by the dead load. All right, caused by the dead load. And next part is the instantaneous deflection caused by the live load. And last part is the time-dependent coefficient multiplied by the deflection caused by the sustained live load. Sustained live load. All right, so that is the definition of total deflection here. That is the definition of a total deflection here. So let me just put a mark here so you know what this content is about. This is deflection component, okay? Deflection component, meaning what the deflection of the beam consists of, right? What does it consist of? So these are the components. Now, the elephant in the room is we have talked about all this, but still one more thing hasn't talked about. What is this so-called lambda as a function of t? What is this time-dependent coefficient anyway? You keep using it, right, without giving me the definition of it. What is it, right? So ACI has given us the explanation, right? So if you see ACI 24.2.4.1, and you see the definition of lambda, all right? And lambda is actually an equation of following parameters. And top is called C is a parameter which is time dependent coefficient. Okay, and bottom here is 1 plus 50 multiplied by rho prime. 50 multiplied by rho prime. Okay, now rho prime is defined as the compressive reinforcement ratio. Compressive reinforcement ratio. Okay, now AS prime is area of compressive reinforcement. Be careful, okay? With prime, everything is compressive, okay? Compressive reinforcement. Okay, so that is this equation. Now, only thing that left defined is this parameter C here, and we call it again time-dependent coefficient. It's a little bit duplicating, but it actually has a different meaning of it. Okay, so this little fellow here, C, we have to define it. Define it. Now, there's no equation for C, unfortunately, from the code. All right, but the code offer you a table. Offer you a table. All right, so if you draw the C in the y-axis and with respect to the time t here, and we draw the x-axis as the time, you realize that this C, if I made a little table here, and you can find the ACI 24.2.4.1, and this tells you that this number cannot exceed 2. Maximum is 2. Okay, so this is 2. And in the middle of it, let's say this is 1. Okay, so here again, this is 1. And this is 2. All right, and then I want to put some marks in terms of x-axis. So this is 0 time, right? And then I have 3 months, 6 months, and 12, 24, okay, 36, and 48, and last but not least, 60. All right. So apparently, if I do the grid, right, I do the grid for the table, that means get all this horizontal and vertical lines and show this gridded table. And my coefficient, time-dependent coefficient in terms of red line will go like this. So before, almost like a linear line here, almost like linear line here, between 0 to 3 months, and this is time in terms of months. All right, so at beginning from 0 to 3 months, it responds almost like linear line, okay? Almost like linear line. Then it takes off kind of like a polynomial, right? Kind of like a polynomial and go all the way up to 2.0. All right, and you cross some of the number here at 6 months. This number here is usually 1.2. Okay, and this point at 12 months is almost 1.4. Okay, so how do we use this table, right? So when you need to compute lambda, right? When you need to compute lambda, you will go to this table, find out the C given the time, given the time. Okay, then you plug in C and find the lambda. You plug in C, find the lambda. Okay, so if this is the case, now let's take a look at it, right? So what is lambda? Sorry, what is lambda? Let's take some example, right? How to calculate? So calculate lambda at t equal to infinity, okay? And at t equal to, say some value here, let me say that t equal to, close this one off first, say 3 months, okay? And let's just say that rho prime equal to a as prime divided by bd here, and assume I have reinforcement as and as prime, and be careful, as prime is the compressive reinforcement, okay? And let's assume this is about 0.01, okay? This is just assumption, okay, given. All right, so how do I compute that? So essentially, I need to find out solve Let's do it together. I need to find out lambda t equals to infinity, right? So when I try to find a lambda equal to t to infinity, I use this equation here, right? So that equals to it cos c at t equal to infinity divided by 1 plus 50 multiplied by rho prime, all right? So I look through the table, I see that when t equal to infinity, right, as approaching 60 and beyond, I said this is approaching point 2. This is approaching point 2, right? So here I say, look, from the table, cos c would equal to point 2, sorry, 2.0, cos c equal to 2.0. This is 2, and bottom here, 1 plus 50 multiplied by 0.01. Okay, so here I have 2 divided by 1 plus, this is 0.5, right? So this is that, okay? And then I have 2 over 1.5. That is what? 2, 4, sorry, 3, 4. So 3, 4, and this is 1.333. So this is lambda at t equals to infinity, all right?
Professor,
Yeah,
what is the symbol you have written on the first line there by, yeah, that one.
okay. So I call it c. I think that's correct, but I may be wrong. So the way I understand is I goes like this, wiggle, wiggle, and goes like that. It's just a symbol. If you go to ACI 24.2.4.1, you see the symbol like that.
Okay, thank you.
Feel better? Okay. I may be wrong in calling it, pronouncing it, but this is the correct way to write it. Okay. If you feel like this is too much, you can write it either way, like this, all right? Or you can use E, it doesn't matter, as long as you know what is representing, okay? It's just a time dependent coefficient, okay? All right. So quickly get back to this. Let me finish this. So lambda now at t equal to infinity is 1.333, right? So what if I change the time to 3 months, let t equal to 3. So let me use this equation, right? So at t equal to 3, my c here, using this table gives me a value of 1. Gives me a value of 1, right? So this equal to 1.0 divided by 1 plus 50 multiplied by rho prime. And rho prime is what? 0.01, right? So 0.01. So this is 1 over 1.5. So this is 2/3 equal to 0.667. All right. So now that is the corresponding lambda for 3 months. For 3 months. Okay. All right. So here, let me make one more example, right? If you take a look at the original equation, right? This says here lambda from t0 to infinity. What does it mean, right? What does it mean? So lambda, if I want to put a problem here, so how about lambda t equal to 3 months to infinity, right? What does this mean, right? This means that lambda 3 to infinity equal to lambda at t equal to infinity minus lambda t equal to 3 months. Okay, so that means in the equation it goes cos t equal to infinity minus cos t equal to 3 months divided by 1 plus 50 multiplied by rho prime. Okay, so you bring the number in, t equal to infinity cos equal to 2.0 minus t equal to 3, that is 1.2, sorry, 1.0, and divided by a 1.5. So this equal to 1 over 1.5. Again, that is 0.667. Sorry, no, 0.333. Is that right? Wait, let me see here. Yes, I am okay. So this is 0.2667. All right. Okay, so that is what it is. That is what it is. All right. So yep. Okay, so this is the lambda between 3 months when the construction is completed, hopefully, and infinity, which is the time the structure stands. Okay, time structure stands. All right. Any question on this? How do we obtain the time-dependent coefficient lambda? Anything? All right. Now, this is quite a simple exercise. All right. For you in the exam, you need this table, okay? You need to find this table ACI 24.2.4.1 and interpolate to find out this coefficient here. And in the exam, we will provide you that table, okay? We will provide you that table. All right. Okay. All right. So that is how we find the coefficient. So now let me give you an example how we find out the deflections. Okay. So with lambda, we can actually calculate deflection on beams, right? Deflection of the beams. All right. Say, let's use the previous example, right? From the previous lecture. We have a continuously supported beam, fixed ends at both ends, and we have a moment like this, right? And the top positive moment here is 162 kPa, and the negative moment at two ends is 225 kPa. Right? That was the moment. And let me give you some loading conditions, right? The dead load, omega DL, is 1.65 kips per linear foot. Okay, and the live load here applied is 3.3 kips per linear foot. And I will also say that 20% of omega live load is sustained. 20% of it is sustained. Okay. Now the question we have is A, what is the long-term, okay, long-term deflection of the beam? Okay, and to be specific, at middle span. Okay, and again, second question is, what is the long-term deflection of the beam at middle span again, caused by the sustained live load, caused by the sustained live load. Okay, so these are two questions we hope to answer. All right, so how to do this? How to do this? First of all, right? First of all, let's remember one thing. So for solve. Okay, now key thing here is to calculate deflection, we need the deflection equation for a fixed supported beam. Okay, for a fixed beam. And that equation is delta equal to 5/48, okay, multiplied L squared divided by a EIE, okay, EIE, and now multiplied by inside is the moment at middle span, bending moment at the middle span, plus a 10%, 0.1, okay, multiplied by the bending moment at the left end and bending moment at the right end. Okay, so to give you a perspective, right, let me draw the structure here. So this is the fixed support, so fixed support here, fixed support here. So the moment, right, the moment goes like this. Let me use a different color, sorry about this. Use a different color, show you the moment diagram. So the moment diagram like this. Okay, and this is M in the middle span. This is M1, and this is M2. Okay, and the length for the beam is L. And now E, let's use modulus of concrete, okay? Don't worry about the steel. Use the modulus of concrete, okay? and IE is the effective moment of inertia. And we calculated this before. Okay, effective moment of inertia. Okay, so that is the equation to calculate the middle span deflection. Okay, and be careful, this is mid span deflection. Okay, so we're going to use this equation to calculate the long-term deflection. We're going to use this equation to calculate long-term deflection. Okay, now first of all, what we're going to do is we have to find out. So A, step number one. So question A, step number one, find delta instantaneous, delta I. Okay, so we know that delta I should equal to delta I dl plus delta I live. Okay, delta I dl and delta ll, right? Live load. Okay, so how do I get this? How do I get this? I first look at the moment diagram. And this is the moment diagram. This is a moment diagram. And this moment diagram was caused by the loading on the right-hand side. So let's say moment diagram gives me an information like this. And the middle span have a positive bending moment that is 162 kip foot. And this is negative 225 kip foot. And this is negative 225 kip foot. And all these moments were caused by dead load, instantaneous dead load, and live load together. I know that. Why is that? Because these are so-called factor moment. Factor moment by this. Okay, right? So that's how we arrive at this. So how to calculate the deflection, the delta instantaneous, then, delta instantaneous I, then immediately I can plug the number in. So that is using this red equation here. Okay, so this equation here, boxed up. Let me say, remember this, right? Remember this. So I'm going to use this equation here. So delta IL equal to 5/48. Okay. Now the span length, right? So let me give you an information. Span length from the last lecture is 25 feet. Okay. This is 25 feet. Okay. So 25 feet. All right. I want to convert everything into inches. So 12 inch per foot. Okay. That is the span. And to the power of squared. Okay, divide by Young's modulus of concrete. Okay, Young's modulus of concrete. So I calculate this out for you. 3600 ksi. How do I get this, right? So E equal to 57,000 square root of prime C equal to 57,000 square root of 4,000 psi. And I got this number 3600 ksi. Okay. All right. Now IE from the previous lecture, that was 12395 inch to the power of 4. Okay, so this is 12395 inch to the power of 4. All right, and now bracket inside. Okay, so take a look at the moment, right? So that is a middle span moment 162 kip foot plus a 10% of left and right hand side, so negative 225 kip foot, minus another 225 kip foot, bracket and outside bracket. Okay. All right. So I lump all the number in. And this is in terms of kip foot, right? And I want to convert back to inches. Don't forget to put a unit here. So let me just organize this better, right? Let me just put down here a little bit so you won't confuse. And this has to be multiplied. This whole thing has to be multiplied 12,000. Okay, 12,000. That is pound per kip. Okay, 12 pounds per kip at inch per foot to get this, right? Convert this unit. So at the end of the day, I got delta I instantaneous deflection that has two parts together, right? ID and I live load equal to what? 0.295 inches. Okay, So this is actually my total instantaneous deflection. So let me put a mark here. So this is total instantaneous deflection, everything, including the dead load induced deflection and the live load induced deflection. All right. But how do I separate them? How do I differentiate them, right? So delta I d dead load should equal to the percentage, isn't it? Percentage. So I'm going to use the proportion of the dead load divided by dead load plus live load, okay? And then multiplied by the total deflection, okay? So that is 1.65 kip per linear foot divided by 1.65 plus 3.3 kips linear foot and multiply 0.295 inches. So this number here equal to a 0.098 inch. And that is instantaneous deflection caused by the dead load. So delta IL, which is live load deflection, right? Live load deflection, that is omega LL divided by dead load plus live load and multiplied by delta I, and that equal to 3.3 divided by a 1.65 plus 3.3 multiplied by 0.295 inch. And I got this number to be a 0.197 inches. Okay. All right. So now we have our total instantaneous deflection and their components of it. Okay. But the question is asking, what about the long-term deflection? What about the long-term deflection, right? So what about long-term deflection? Okay. What about the long-term deflection? So to get the long-term deflection, that is, we want to get delta infinity. And using that equation, that is lambda infinity, okay, multiplied by delta I dl or d, that is instantaneous deflection caused by the dead load, plus delta I live load, instantaneous deflection from the live load, and plus a delta lambda, right, lambda, that is T naught infinity. And this is the time when sustained live load is applied, okay, till the building collapses, and multiplied by the delta instantaneous deflection caused by the live load sustained. Okay, so that is a long-term deflection. That is a long-term deflection. Okay, now to do this, right, I need to compute my coefficient first. So lambda infinity equal to c t equal to infinity plus divided by 1 plus 50 rho prime. That's rho prime. Okay, and now we know that in the previous sections, no compressive reinforcement is present. Okay, no compressive reinforcement. So that means rho prime equal to 0. Rho prime equal to 0. So instantaneously, top here is 2.0 from that tiny little bit table here. Okay, this is 16 months, which is infinity, like long time, right? So that is 2.0 at the top and divided by 1.0, so roughly 2. Roughly 2. Okay, so another lambda t naught infinity, right? T naught infinity, that is 2, sorry, that is c at t equal to infinity minus c at t equal to t naught. So what is T0, right? T naught. That is time when sustained live load is applied. And when the sustained live load is applied, the sustained live load was applied at the very beginning. And we will tell you that in the problem. In this problem, we know that is sustained live load applied at the very beginning, okay? So that is that divided by 1 plus 50 rho prime. So this is 2.0, lambda at t equal to infinity is 2.0 minus this fellow here is 0 and divided by 1. So again, it is 2.0, right? 2.0. Okay. But one more thing. I want to find out the deflection caused by the sustained live load and this is instantaneous deflection, right? I means instantaneous deflection. We know that only 20% of the live load is sustained. So 20% of the instantaneous live load caused the deflection gives me that. So this is 0.2 multiplied by 0.197 inch. Okay, where does 0.197 inch coming from? That is, ladies and gentlemen, we already calculated from A. Okay, from A. All right, so this is the deflection caused by the sustained live load. So now delta infinity means long-term deflection, right? Equal to 2.0, okay, multiplied by the instantaneous deflection caused by the dead load, which is 0.098 inch, okay, 0.098 inch, plus instantaneous live load caused the deflection 0.197 inch, plus 20% of the sustained live load. There's a coefficient in front of it, don't forget. So 20%, 0.2 multiplied by 0.197 inch. And now I have my total deflection to be 0.472 inch. Okay. All right. Now looking back at the problem we're trying to solve here, A is to find out long-term deflection of the whole thing, right? So that is 0.472 inch. B is the long-term deflection caused by the sustained live load. So that is lambda infinity multiplied by the sustained live load caused instantaneous deflection. So this 0.2 multiplied by 0.197 inches. Okay, so this is roughly equal to 0.0. Okay, let me see, 20% of that. So 0.04 inch, roughly. Okay. All right, so now we know how to calculate deflections. Okay. All right, so I'm gonna stop here. Any questions on this deflection calculation part? Okay, you're welcome to stay behind if you have more questions. And if you have any other issues with homework, grading, anything like that, also you can stay behind. All right, but we're done with the deflections. And I see you on Wednesday talking about our next adventure. Okay, thank you. I do have a chat question, I believe. Okay. Stop recording.